Action. First of all, let me thank the organizers for this wonderful conference, and thank you, Raoul, for your kind invitation. And thank you all for staying by for the last day or last afternoon of this day conference. So I'm going to present recent work done with my PhD students, Mona Ben-Derwish, who defended her PhD thesis last December. And she worked on multi-level Monte Carlo, especially pricing barrier options on singular stochastic differential equation. Like main examples we keep in head is the Cox-Singer laws and the CEV models. And then the last part is about extension to Heston model. So the outline of the talk, there are two main parts. The first one is one-dimensional setting. So where we will deal with this kind of stochastic differential equations that may have coefficients that are not locally Lipschitz, so not globally Lipschitz. And the second part of the talk would be the extension for two-dimensional. And of course, one natural extension is to work for a higher dimensional setting. We start with the first thing, one-dimensional setting. So this is what I'm using multi-level Monte Carlo. So I'm interested in pricing down and out barrier type options. As you can see, so you have your European type payoff. It could be a call or a put, but there is a running infimum or running maximum. So it's quite close to the problem mentioned by Mike. So where you have an indicator. So he mentioned the digital option where just the value of the process at terminal time t is involved. But here we have a bit more, since here we have a running minimum or running maximum. So let's assume that you have a kind of one-dimensional diffusions with two coefficients b and sigma, and the coefficient sigma is supposed to be locally Lipschitz. So the main idea is to start from transforming this stochastic differential equation thanks to a Lamperti transformation. So the Lamperti transformation, once you have 1 over sigma to be locally integrable, so you may apply Ito formula for this new function phi, which is the antiderivative of 1 over sigma. And what Ito formula, you realize that your noise become additive. And this is quite important in our setting here in order to run multi-level Monte Carlo in optimal way. So this additive noise is important, but the drawback is that the drift here L may be more, if we have to pay attention for the drift L, since it, of course, the singularity, if it was in the diffusion, then you move it to the drift. But what I'm going to show you today is that moving the singularity to the drift is still better. We can handle with it. However, keeping it in the diffusion coefficient, of course, we may face a lot of trouble. So once I did my Lamperti transformation, of course, my first price may, the initial problem may be reformulated as follows. So we are working on the Lamperti space. And so the running infimum now and the running maximum is on the Lamperti diffusion line. So of course you have to change your payoff, but you are still dealing with barrier type options. So so let me assume so that here I consider the same setting in a paper 11 years ago done by Alfonsi, where he worked on this type of diffusions with additive noise and with drift L that may have one-side Lipschitz assumptions like this one. So we assume that we are one-sided Lipschitz. More than that, we assume that this v of x function that are, of course, built from your drift satisfies a limit to infinity when x is close to 0. So let me stress on the fact that I'm working on positive, I mean, valued differential with additive noise. And thanks to this H1, this guarantees, of course, that your process, thanks to the classical Feller test, you check that your process stay on 0 plus infinity. So we have a strong solution under these assumptions. And this is my general setting. So the idea by Alphonse is to consider, since we have, of course, we have additive noise. So one can think that applying simply an Euler scheme is enough, right? Because since you have additive noise, then your strong error is, of course, of order 1, so which is optimal compared to the Euler in the multiplicative case, which is, of course, of order 1 over square root of n. So, but Alphonse digged a bit more in this direction in order to guarantee the positivity of the scheme. So he kept this in mind, and he introduced this kind of implicit, as you can see here, implicit scheme. And he showed that this scheme, under these assumptions that I showed you, the scheme admits a solution that is still positive. And of course, this has a lot of advantages, and I will show you one main advantage of such a scheme in pricing barrier options. So if you want to guarantee a speed of order 1, here strong error of order 1 for your implicit scheme, so Alphonse, of course, assumed that he has this H2 assumption where he looked to moment, okay, moment of the derivative of L times L, second derivative of L, etc. So under this assumption, you guarantee that your positive numerical scheme have order 1. So starting from this, since we want to deal with barrier option, there was a classical idea that I'm going to explain more in details. It's that can be combined, of course, when pricing barrier option, is to use the Brownian bridge technique in order, of course, to avoid, to take into account what happened between two time discretizations for your scheme, unless, of course, discretizing the running or maximum or the running minimum by discrete running maximum or running minimum. It's better, of course, to use this Brownian bridge. So I'm going to give more details about this Brownian bridge technique. So actually, the Alphonse scheme that I showed you here cannot be applied in the Brownian bridge case, because in the Brownian bridge case, you need to know the points. I mean, it's conditioned to the points in the interval. So you have the YNTI and the YNTI plus 1. So that's why we modified a bit the scheme and we introduced it. So this is, of course, a possible interpolation of the scheme. So we proposed a different one, which is we start from the same discrete scheme here. We start from the same discrete scheme, but for the interpolation, we fix still the coefficient here. So this is essential if you want to run a Brownian bridge behind. So this is a bit different from Alphonse setting. So as I said here, the main advantages of this Brownian interpolation is that first we prove that we keep the same rate of convergence, but the second is, of course, you can combine this with your Brownian bridge trick. So in order to prove that this new scheme, of course, preserves the strong rate of convergence, to strengthen a bit the assumption by Alphonse. So I'm assuming now that my function or my drift L is of order C2 on, of course, 0 plus infinity. And I suppose here that it is decreasing on near 0 and with a bounded derivative outside. So think for 1 of x. L of x is essentially 1 over x. So thanks to the assumption, and of course the previous one that I showed that guarantees that your process is still in 0 plus infinity, we prove that you keep actually the rate of convergence of order here. The strong rate of convergence is still of order 1. So thanks to this theorem, you easily can deduce the corollary here if you want to have moments. So this is also useful for the multi-level setting to guarantee finite moments for your scheme. So we need this fourth assumption here, H4, that is given here, means that y times L have a quadratic linear growth. Quadratic growth, sorry. So this is the scheme. So let me now show you how we run the Brownian bridge technique plus the multi-level Monte Carlo. So let me go back to my starting point, which was pricing this barrier option. So now what I did here is I changed of course, the main diffusion by its approximation scheme here, y bar nt, the scheme that I presented you that is derived from Alfonsi approach. So until here, nothing is lost because I'm just saying that the running minimum here is just the product of n running minimum, but it's not here the discrete, since here I keep track of what's happening between two discretization times. And thanks to the Brownian bridge technique, since y bar nt, if you have a look here, so as you can see, thanks to the scheme, conditionally on the y bar nti here, this point here, and y bar nti plus 1, you perfectly know the distribution of this y bar nt. So you can then run, because it's essentially some drift that you can kill thanks to Girdanov transformation, plus some Brownian increment, and the Brownian increment, the running minimum or running maximum here for the Brownian increment is well known with explicit expression. So mainly this is what happened. So that's why keeping a y bar nt like Alfonsi did here is not helpful. So then thanks to this observation, it's possible to rewrite, I mean, thanks to by induction, by conditioning every time by 2 by 2 on the discretization grid here, you can use the power property in order to derive this expression. So as you can see here, this product of indicator becomes this product of these probabilities, and we have explicit expression for the weights q bar I. This is thanks to the expression coming from the explicit form of a running minimum, continuous running minimum Brownian motion, or Brownian increment, if you want. So conditionally to the 2 points here, y bar nti and y bar nti plus 1, I know perfectly. I don't miss any information for what's happening between these two discretization times. Sorry. So you can have the same, of course. It's symmetric. You have this is for the down and out and for the up and out. So when I look into the bibliography, so I think the first paper I saw is the one by Baldi in '95. And there is a nice paper by Emmanuel in 2009, who, of course, gave an overview of these techniques with some enhanced and refinements behind the Brownian bridge technique. So, of course, today's agenda is how to make this work with multi-level Monte Carlo. So I think most of you were here for the talk of Mike Giles. So the idea is, of course, of the multi-level is to be able to rewrite this equation 6 here. You write the price as follows. So you start from a very coarse approximation. I mean, the time step of order 1 here, a very rough approximation, and then some correction, L exactly correction, and having a finer and finer time discretizations here. And of course, as shown by Mike in his talk today, of course, this, of course, beats the classical Monte Carlo in the setting of discretization schemes. So the idea now is how to deal with this, of course, this running minimum or running supremum with this product in order to properly implement the multi-level Monte Carlo. So the first thing to do is, of course, to rewrite this thanks to the Brownian bridge. So we start first with the finer approximation. So this is the easiest one because it's the finest grid. There is I mean, you have all the increments for this finer grid. So if you have these increments, then thanks to the proposition I showed you, you can simply write your Brownian bridge. I mean, this is a representation of the barrier price option for a finer time discretization, which is of order 2 to the power L. So, and the problem comes when you want to write your coarse approximation. Until now, it's okay. It's just readapting with this new time step, 2 to the power L. The problem starts when you want to derive the coarse approximation that comes, because of course, what is essential to say is that, of course, each expectation here is approximated independently, but in one block of expectation, of course, the paths, the Brownian path that you use for P bar L minus 1, for P bar L, have to be recycled to sample the coarse one. So this is the essential trick in multi-level Monte Carlo. So for the coarse, and especially for barrier option, if you do it in a naive way, means just summing up the Brownian increment, of course, your multi-level Monte Carlo won't work. However, Mike comes in a recent paper, 2019, not recent too much, but he said, for the coarse scheme, he proposed to use an extra conditional point in your conditioning in order to get the product. So here you have the coarse grid. So the classical one would be you condition simply with the first point here and the third point coming from the coarse grid. So Mike Giles proposed to add the third point, which is still your coarse scheme, but evaluated at the point in the middle between the two. So means in the point in the final grid between your between Ti L minus 1 and Ti plus 1 L minus 1. And this helps a lot because you have more information, as you can see. And I will give you some intuition that comes from the proof we wrote here, why also this is helpful. Because there are some observations to be said here. So, if you do that, then you can split your indicator in two pieces, okay? Since your coarse interval still in the coarse approximation is split it in two, and then you run twice your Brownian bridge trick in order to get similar expression as this. One can wonder, you have to take one good interpolation. If the good interpolation is not chosen, of course, you can't succeed to run a successful multi-level Monte Carlo. And it turns out that our scheme, the interpolation I showed you before, works well for this technique. Okay, so then the idea, of course, you run twice, as I said. You wrote here your scheme for the course here, and you want to evaluate the supremum over the first or the last time interval, for example, here. And of course, everything is frozen since it's conditional, except the Brownian increment. So this term can be killed thanks to Girsanov transform. And finally, it remains to use the explicit law of the Brownian increment, which is well known. And you should do the same thing for the other piece of the interval. And finally, you end up with here, for the coarse approximation, you end up with the product of here. Of course, the I here runs on the coarse grid. So that's why you see 2L minus 1, not 2 to the power L. But you have product of two components, and this helps a lot. So these two components comes from the Brownian, of course, from the Brownian bridge technique. And you can, again, write the whole thing on index I that runs now on the finer grid. So you are still in the course, but your index here, I, is of course running on the course. And this helps a lot in the analysis, right? Because you are treating difference of products, and you want that your products have the same number of terms. So this is the main, of course, idea here. now you can, thanks to this, you can write your multi-level Monte Carlo. So each expectation, as I said, is going to be approximated independently. And in one given expectation here of order L, of course, I will use what I showed you before. Here's the finer, and this is the coarser that I get from the finer, thanks to this 3-point conditioning I used here. So this is the other, of course, estimator if you use for down and out, and this is for the up and out. So let me recall what Mike showed us today. So in order to study the multi-level Monte Carlo, you need, of course, to first check that is telescoping some. So this is the case. Then you have to check the weak error that you have. So here the weak error is given by HL to the alpha. And you have also to check the strong error. So the strong error here, the parameter for the strong error is the beta. And it turns out that from Giles, Mike Giles' work, that if you want to achieve the total error of order epsilon, means the mean square error of order epsilon to the square. So this is the optimal complexity that you would get for a multi-level. So it is of order epsilon minus 2. If beta is larger, strictly larger than 1, epsilon minus 2 with a log, of course, and here with some power of epsilon if beta is between 0 and 1. And all this, of course, is still better than the Monte Carlo setting, if optimized, of course, because the complexity in this case, if you want to achieve such a mean square error, the optimal Monte Carlo complexity is of order epsilon minus 3. So you're still beating the multi-level. The multi-level still beats the Monte Carlo. So in order to study, or so what we need is actually the weak error is known, right? Because the essential thing here is to derive the variance here. So it means the strong error. This is essential. So I want to derive the variance here of a given difference in a given block. What is the order? So because in order to find the corresponding beta, and depending on the quality of the beta, your approximation would be good or not. Of course, we are expecting the optimal regime is corresponding to beta strictly larger than 1. In order to do that, in our case, we needed to study what we call the extreme paths. So Mike mentioned this in his study. He said staying close to the boundary, inner and outer the boundary, same problem. So, but we needed to derive this for, of course, the scheme that we have. And more than that, we are not in a case where your diffusion has a global Lipschitz coefficient. So you have this singularity that comes from the diffusion coefficient. So we have to be careful while doing this. So first of all, we need to control the moments here. So this term, where you have the true diffusion and both schemes, the finer and the coarser, could be, I mean, if you want them larger than HL minus eta, so this probability could be as small as you want. Q is arbitrary. Why? Because you have finite positive moments. So think of a Markov inequality for this, and then, of course, there is no restriction. Same thing here for the difference. We need to study how extreme could be this difference between the scheme, the true diffusion, and between the finer scheme and the coarse scheme. How is this? And this could be made very small as you want, since Q is arbitrary. However, we found one term that is a bit annoying here, is this one. We have to control the extreme path, of course, of the term that comes from the drift. And as I said, thanks to the Lamperti transform, we just switched the problem from the diffusion coefficient to the drift coefficient. And of course, but we could handle it. And the extreme here path, yes, we can study the extreme path given by the drift term. It's small, but not small too much. So Q is not arbitrary. It should be between Q and P of eta. P is the one, if you remember, that the order that are satisfied here, the moments, the order, the finite moments satisfied in assumption H tilde 2, H3, and H4. So we have restriction. This is what I want to say. So if you work in globally Lipschitz coefficients, you don't have this problem. All the terms could be made as small as you want. But in this case, special case, of course, you have restriction on the moments. So, and this is the main theorem of the first part. It says the following. So assume that your payoff function G satisfies kind of this locally Lipschitz condition, and it has a polynomial growth. So if it is the case, then if your assumption H tilde 2, H3, and H4 are satisfied for some P, and if this P have this lower bound here for some delta in between 0 and 1/2, okay, so this is the first step. The second step, as mentioned by Mike today, you need that not the diffusion has a density, but the infimum in my case. So the running infimum or the running supremum of the diffusion YT, the true diffusion, there is no scheme here, has a bounded density in the neighborhood of the singularity, which is, of course, the barrier, right? So if such assumptions are satisfied, you can see that your rate of convergence beta is 1 plus delta, okay? Is 1 plus delta, and this is enough to make the multi-level optimal, because beta have to be strictly larger than 1. So I needed just a strictly small delta for which I achieved this rate of convergence for the variance. So a first remark. So if we combine this, of course, with the theorem I showed you before, the theorem of complexity, of course, we have the optimal regime for the multi-level Monte Carlo, epsilon minus 2. And this, it's like you have a Monte Carlo, an unbiased Monte Carlo, right? Because you can forget about your approximation scheme. And this is wonderful. The other remark, of course, you don't have to look for delta too large here. Why? Because otherwise you will have a lot of restrictions on your coefficient in the moments here you would achieve. So it's not in your, it's not a good thing to look for, it's not a good thing to look for large delta. Let me just stress the fact that if you are working with global classical diffusions with globally Lipschitz coefficients, then the order achieved here in the Mike works is 3.5. So delta is equal 1/2. However, I can do this in my case, as you can see, my moments explode if I do that. Okay, so I summarize the proof in 3 main steps. So the first step is how to deal with extreme paths first, and then the non-extreme path. So for the extreme path, we are based on the estimates here. And mainly this is what appear when you analyze your difference scheme. This is what appear. So imagine that I put all these events in one set and then try to work with it. So, so for the extreme events, it turns out that on the extreme events, this variance is of order Q to the HL to the power Q over 1 plus gamma, still having this restriction on Q. The second event, we can manage it. So we are non-extreme, and the non-extreme path, we split it into two small events. The events that the running minimum is far from the boundary, and the second event is, of course, the complementary. So this is what mainly discussed by Mike in his morning talk of this morning. But instead of the infimum, he had ST, since he was interested in digital option rather than barrier option. So we can make this term as small with this order. And the third term is still the non-extreme event, but the complementary of the second one. And here appears, if you write together the difference of the product, so you are happy because your both products, the one coming from the coarse from the fine approximation, and the one coming from the coarse approximation, you are happy because they are have the same number of terms. And so you can do a nice analysis. And now, thanks to the probability of this third event can be estimated if you know that the running infimum has a continuous density near the neighborhood. So if it is the case, then you put all this together and you end up with the condition that I showed you. If you want to achieve for all the three terms I showed you, 1 plus delta, and put all together the conditions, what comes out is this condition on your P. So that have to be, of course, satisfied. So let me show you a first application of this general result. The first application I have in mind is, of course, the Cox-Ingersoll loss model. So in this setting, here is the this is a locally Lipschitz, of course, coefficient. So I'm assuming the Fuller condition so that to guarantee the positivity of my process. So, and then thanks to the Lamperti transform, you get what we call a kind of Bessel process. Here you have additive noise, and then here you have a nice term, which is linear, but you have 1 over y. So this is how you switch your singularity from the diffusion to the drift, for example, for the case of the CIR. And then, of course, you are now interested in pricing this new payoffs in this case, where now you are on the Lamperti space. So, so this is the list of the condition that you have to check. The first one is the H1, H3, and H4I are straightforward things, since we have this slightly strengthened assumption for the coefficients. And the H2, if you remember, I needed movements here involving the derivative of the drift and the drift times the drift. So if you put all this together, you would need to achieve a finite moment on your CIR process of this order. Okay, but we have clearly know everything about Cox-Ingersoll process. We know when the negative it has finite negative moments, and it turns out that of course it has finite positive moments and few negative moments, depending of course how you choose and of course, you put all this together. So we have lower bound in our case here for the condition. So we should have, if we choose A and sigma such that this condition is satisfied, means slightly larger than 18. So it's quite restrictive, but still works. Of course, then you are in the setting of the mean term I showed before. Except you need to check why the infimum of your process or the supremum of the process of mainly the Cox-Ingersoll process has a bounded density in the neighborhood of the barrier. And looking in the literature, I didn't find any results in that direction. So we prove it in this work. So let me here show this results. So yes, when you are interested, of course, in studying Laplace transform or any, transformation of the CIR process, clearly you would need the special functions naturally appears. So what we showed here is that for the Cox-Ingersoll process, the supremum has a continuous density on a compact set, K, that is included in the interval, of course, open set here, x0 plus infinity. And we derived semi-explicit form from the density of the CIR. So this is for the running supremum. And I will give you maybe a few details how this comes when I studied the running minimum. Actually, it comes from, there is a clear connection between, if you look to the stopping time, the first time, so you start from a point which is larger than the barrier Z, okay? And you want to characterize the first time where you hit the barrier. So you start above and you want to check what. case where we've been lucky because we have explicit solution in this case. We didn't need to run any extra numerical effort in order to deduce the solution of your implicit scheme. So here it's explicit and it's positive, so it has nice properties. So this is what we obtained. So we found in the literature this paper from 2001 by David Bandinsky, who were interested using deterministic approaches, numerical approaches, in order to price the same barrier option on CIR and CEV. CIR, sorry. So it turns out that they have a benchmark price in their case. So we followed this case and we compared both the multi-level Monte Carlo cost and the Monte Carlo cost, of course. The gain here is the saving. As usual, when you ask for high accuracy, of course, you have a higher saving, like for standard multi-level Monte Carlo. And here are the graphs we obtained for both down and out and up and out options. So as you can see, here is the epsilon squared times the cost. So it is constant, means that your effort of the multi-level, which is in red, is really the perfect optimal cost, epsilon -2. And you can see that your multi-level is increasing, of course, surely like epsilon -3. So we applied the same thing for CEV, but for CEV, it's again more challenging. Why? Because of the power alpha here. So there is a power alpha, so you have the choice either to work with alpha between 1/2 and 1 or alpha larger than 1. So in our case, we choose to work on alpha larger than 1 since we have positivity of the diffusion in this case. Otherwise, you would do all kind of drift positive if you want to guarantee such positivity. So thanks to the Lamperti transform, again, this is the drift we obtain. And we've been here still lucky in this case because we have still 1 over y and a linear term and 1 over y. So like before means that if you run your implicit scheme, you are going to have explicit solution. You don't need to run any, numerical approximation of the solution of your implicit scheme. So in order to deal to the moments, so there is nice properties from CEV, you can move to a Cox-Singer-Selros. And since all the moments of the Cox-Singer-Selros are well characterized, so means that for the CEV, they are all well characterized. So that's why we checked all the conditions we have and put them together. And it turns out that we wrote a different theorem. Why we wrote a different theorem? Because now the behavior of the payoff is not like before. Since for the CEV model, if you write g of x minus g of y, this is the upper bound you get. So you have negative powers of x. So we have to deal with negative powers. So of course, this is a different theorem from the setting that I showed before. So, but for the special setting of CEV for the CEV model. And this is our new assumption that we have to take into account if you want, of course, to study the problem of extreme path for your CEV. And the variance, the good news is that the variance is still of the good order, 1 plus some delta, positive delta, but still the price to pay is that the infimum, running infimum of YT is, in this case, we could not result for the supremum because the estimates are in the wrong sense. If you want to deal with the, it's down and out and not up and out. So we came up with this condition in this case. So alpha is really close to 1. It's really close to 1. And the other remark, okay, you may choose alpha between 1/2 and 1, okay? But then you have to add the positive drift, as I said, but I don't know any result, and I don't know how to show that this running infimum for xt or running supremum for xt has a continuous density. I have no idea how to deal with this, or to deal with this problem. However, if you assume that a equals 0 and take alpha larger than 1, then you are able to handle and prove that this running infimum and even the running supremum have, in this case, bounded density. So this is what we show. Still, we have explicit Laplace transform of these stopping times that we've been able to deal with. So this is the explicit density for the CEV model. So it has two expressions depending on positive mu or negative mu. And we did the same thing because we still have explicit expression for the stopping time where your initial condition is above the boundary. So we have still explicit for the variance. As you can see, and as mentioned by Giles, you need this existence of density in order to deal with the order or the behavior of your approximation when it is near or close to the boundaries. So let's move to the numerical test for this case. As I said, since the drift is quite simple, we have explicit solution for the implicit scheme here. This is our new payoff. There is no benchmark price in this case, but we tested for reasonable values, but of course not satisfy our assumptions. We tried them for a condition that would not satisfy our theoretical assumptions. And here we obtained very amazing results here. For example, the savings are larger than for the CR in this case. As you can see, it may reach 8,000 when you ask for an accuracy of order 10 minus 4. For the up and out and for the down and out, it may reach 2,500 times. So this is, and you can see here, the effort for the multi-level is more flat than the CIR, if you remember the previous curve. So this is quite amazing. And of course, the Monte Carlo is still behaving like epsilon minus 3. So this ends the first part. So I have a minute, I guess, or to show you a more challenging problem is what about high dimension? And let's start with the first problem is two-dimensional problem is Heston model. Now let me show you the problem I faced when I treated this with Muna. So in this thing to do to avoid a moment explosion because it you know that clearly from the previous study you need finite moments for your scheme, for your diffusion, etc. For the Heston, of course, you are restricted in terms of moments. So in order to deal with this problem, we first restrict ourselves to work with the log-Heston, the log price, which is common in finance. So we have one component here with Brownian for the common Brownian for between the volatility and the price, log price, and of course an independent Brownian motion here. And the idea is, how could we find a scheme that could work for our, how to say, bridge technique, a Brownian bridge technique for the Brownian, for the setting of barrier option. So I will show you an alternative approach. And so if you don't really use the proper scheme with your multi-level Monte Carlo, you won't succeed to have, nice results. So, but we are really motivated to, find the scheme that makes the proof work. This is was my main motivation. So the thing is, the idea is not to introduce a scheme for VT. Otherwise, it's clear I can quickly lose in the analysis of the extreme path. So the idea here is to explicitly or simulate here the Cox-Ingersoll process component VT, thanks to the known expression. You know that it is given the VU, of course, U smaller than T, then you can derive, thanks to the component VT, thanks to the K2 or K-squared random variable. We know it's completely explicit. So this is the first idea. And then first we rewrite our log-Heston price as follows. So I replaced the Brownian increment that comes from the volatility here. I replace it by of course, the diffusion VT, thanks to the SDE, right, coming from the Cox-Ingersoll-House process. So here is the row component, and I have an independent component. So this is what I used. I used that this integral that is common, right? It's common to both the log price and to the volatility model is explicit. So if you know explicitly VU, VT, then of course you can simulate this term. So in what follows, I will assume, of course, here the Feller condition that still holds to guarantee the positivity of my CIR process. And let's have a look to the scheme. So the idea here is we use the scheme is called the semi-exact log-Heston. Means that for the log price, I'm using a kind of Euler scheme here, and then defining an interpolation. And for the V, I simulated exactly. So I need just my points VTI for each point in the grid here. So this is the scheme. This replaces, as I said, the Brownian increment, right? And based on the ideas in this IIR, so the first part of the talk, we come with this interpolated semi-exact log-Heston. So it seems that this interpolation is very helpful for the proof if you want to quantify the variance for your multi-level, especially when you treat the extreme parts I showed you like before. So it turns out that the proof is okay for this scheme. So this scheme is now called the interpolated semi-exact log-Heston scheme. So as I said, the main advantage is that, of course, Brownian bridge interpolation, the proof for the variance is okay. So the bad news somehow is here. For this scheme, your speed, strong convergence rate is square root of 1 over square root of n. So this is not surprising, right? Because you are using Euler scheme. So it's not surprising at all. And I will show you that actually in numerics, it's not so bad. So let's look for the Brownian bridge technique. So here we wrote the same arguments as before, but for log-Heston price. So now the problem is that your running infimum and your running maximum is on the log price, not on the CIR process. So this is a main difference between the first part and the second part. And so now if you use the Brownian bridge technique for the log price, this is what you obtain. And you can see here, this is VTI. So VTI appears in the denominator of this expression. So I need the positivity, not only positivity, I need finite negative moments then when I want to treat and a lot. So among these things, so this is the multi-level Monte Carlo simulator, as you can see here, where I use the same recipe, let's say, using several points conditioning in order to come out with this expression for my Brownian bridge. So here, we not only condition it, it's a 4-point at least, it's even or 5 points conditioning. I condition with respect to the main point in the coarse grid, with the middle point, like I showed you before, for X, and add to that the 2 points of the V process on the TIL-1 and TI+1 n-1. Because in my scheme, if you look carefully here, appears these 2 points. So the idea is, of course, to freeze everything here. This is the idea of Brownian bridge. You freeze everything except, of course, your Brownian increment because it's explicit. So you need 5 points conditioning here trick. So, of course, we checked that we have the telescoping properties satisfied. We wrote the same thing for the here up and out. So using the same trick. So I mean, the Brownian bridge works well with this scheme. And this is what appears in our extreme path. So there are two types of extreme paths that appears in this study. The first one is dealing with X. So for X is okay because we have finite moments. So for the log price, these quantities could be made the extreme path here, the probability to be extreme could be made as small as possible since Q is arbitrary here. However, the problems start here. In your analysis, as you have in this product, the VTI in the dominator, you have to control these terms. And here the problem starts. So of course, when you have negative moment, you have restrictions known from the Cox-Ingersoll process. This is known. For the other two terms, it's okay, since we deal with positive moments. So this extreme path could be made very small. However, those terms are not so much extreme, actually. So we applied here, of course, we assume that we have a Lipschitz payoff. We don't have the, of course, we do not cover the exact Heston, but log-Heston model. We are only able to prove that the variance is of order 1/2 minus delta for delta, of course, in this range, where A, so there is a condition on A, of course, and delta. So it means that your variance is not optimal in order to achieve an optimal regime, the optimal regime for the multi-level Monte Carlo. So in the literature exists an alternative method known for the Heston model is known by Mike Giles and Lipschitz. They introduced what we call the antithetic multi-level Monte Carlo. I guess everybody, or most of you are familiar with the antithetic, where you introduce Milstein schemes for the Heston price instead of Euler scheme, and for both here, it's a Milstein scheme of course for two-dimensional process, but for which you removed the living area. So this is well known. And known that if you use such a multi-level antithetic multi-level Monte Carlo for pricing European option on the Heston model, of course, you are in the optimal regime. They show this in their paper. So one can wonder, what if I try the schemes numerically, not theoretically, because we're not able to prove anything on their scheme. What is the rate of convergence for barrier option in this case? I hope we got the slides in a few seconds. So yes, thank you. So bridge written for the antithetic multi-level Monte Carlos. The estimator for people who know the antithetic, you recognize immediately this approximation. And with what we got at the end for the semi-exact here, surprisingly, we reached a very small MLMC complexity close to the optimal regime. However, for the antithetic, we are clearly not far from Monte Carlo. So it's a 2.5, which is still better than Monte Carlo. But surprisingly, the scheme we designed here achieved better results. So we can have a look on the curves here. So this is for the antithetic. So the effort here for the antithetic, as you can see, is epsilon. So complexity is epsilon to the minus 2.4, let's say. And the complexity here for our designed scheme, the semi-explicit scheme here, is of order epsilon to the power minus 2.3. So which suggests that our theoretical result, we are skeptical, right? So means that portion is still open, right? So for the paper for the CIV and the CEV and CIR can be found on the archive. And thank you for your attention.